Hello there, and welcome. Tonight I want to take you somewhere quiet, somewhere gentle, to the warm edge of our own star, where a mystery moves softly in the light. It's a place you've felt but perhaps never truly considered. That space between you and the sun where something remarkable happens every single moment. Something so profound yet so peaceful that it touches everything you've ever known without making a sound. I want to talk with you about something that might seem impossible at first. Something that sounds like it shouldn't be true, but is happening right now as we speak together in this quiet moment. Our sun, that steady companion that has risen and set throughout every day of your life, is losing 4 million tons of mass every single second. 4 million tons! Imagine that for a moment. That's the weight of about 40,000 blue whales, or 800,000 elephants. Or if you prefer something more tangible, it's like the sun is losing the equivalent mass of Mount Everest every few hours, just dissolving into space, transforming into something else entirely. But here's what makes this beautiful rather than alarming. This loss isn't a vanishing, not really. It's more like a soft donation, a gentle giving that the sun offers to the cosmos, and ultimately to you and me. This mass doesn't disappear. It becomes the light that's perhaps touching your face right now if you're listening during the day, or the stored warmth in the ground beneath you if night has fallen where you are. It becomes the energy that drives every wind, every current in the ocean, every photosynthesis reaction in every leaf on every tree you've ever seen. The sun is literally becoming lighter so that we might live, transforming its very substance into the possibility of everything we know. And this has been happening for billions of years. This quiet arithmetic of existence playing out second by second, never rushing, never pausing, just continuing with a patience that human minds can barely fathom. As we settle into this story together, as you perhaps adjust your pillow or pull your blanket a little closer, I'd love to know where you're listening from tonight. What time is it where you are? Are you watching the last light fade from your window, or has darkness already wrapped around your part of the world like a comfortable old coat? There's something beautiful about knowing that wherever you are, whether it's a bustling city or a quiet countryside, whether it's winter or summer where you sit, we're all circling the same star, all receiving the same ancient gift of transformed mass becoming light. And if this gentle exploration brings you some peace tonight, if these thoughts help quiet your mind and ease you toward rest, perhaps you might consider subscribing so that future nights can find us together again, exploring other mysteries of our cosmos. But only if it feels right, only if it feels as natural as breathing. There's no urgency here, no pressure, just an invitation as soft as starlight. You know, when we think about the sun, we often think of it as permanent, unchanging, this eternal torch in the sky. Our ancestors built monuments to track its movement, created entire mythologies around its daily journey, and even today we set our clocks by its rhythm. But the truth is far more interesting than permanence. The sun is engaged in a constant act of transformation, a continuous becoming that involves the most fundamental equation in all of physics, an equation so elegant and simple that when Einstein first wrote it down, he couldn't have imagined all the ways it would reshape our understanding of the universe. That equation, E=mc², isn't just some abstract mathematical concept locked away in textbooks. It's happening right now inside our sun, governing this gentle loss of mass we're contemplating together. Think about what 4 million tons per second really means. In the time it's taken me to share these thoughts with you, perhaps a minute or two, the sun has lost the mass equivalent to a small mountain. By the time you wake tomorrow morning, if you sleep for 8 hours, the sun will be lighter by about 100 billion tons. And yet, when you open your eyes and look at the sunrise, it will appear exactly as it did this morning, and yesterday morning, and every morning of your life. This is the remarkable stability within change, the constancy within transformation. The sun has been doing this for about 4.5 billion years, and it will continue for billions more. This patient conversion of matter into energy, this slow, stellar metabolism that makes everything else possible. What fascinates me most about this process is how quiet it is from our perspective. There's no drama to it, no sudden flashes or cosmic announcements. The sun just continues its work, fusing hydrogen into helium in its core, a process that happens at temperatures of about 15 million degrees Celsius, pressures beyond anything we can create on Earth, and yet from our distance, we experience it as nothing more than gentle warmth and soft light. It's like the universe's most powerful nuclear reactor is running continuously, just 8 light minutes away from us, and we experience it as the gentle touch of morning sun on our skin, the golden hour that photographers love, the warmth that makes cats seek out sunny spots on the floor. Let me paint you a picture of what's actually happening inside our star right now, at this very moment as you listen. Deep in the sun's core, in a region that extends about a quarter of the way out from the centre, conditions are so extreme that the normal rules of matter break down. Hydrogen nuclei, simple protons that would normally repel each other due to their positive charges, are pressed together with such force that they overcome their natural reluctance to touch. The temperature there is about 15 million degrees Celsius, which sounds violent, but think of it more as a cosmic kitchen where the universe is slowly cooking up the elements that will eventually become planets and possibly life. The pressure is about 265 billion times greater than the air pressure you're experiencing right now, wherever you're listening. In these conditions, something magical happens. 4 hydrogen nuclei gradually combine to create one helium nucleus, but the helium weighs slightly less than the 4 hydrogen nuclei that went into making it. That missing mass, that tiny difference, doesn't disappear. It transforms into pure energy according to Einstein's beautiful equation. And when I say tiny, I mean really tiny. The mass difference is only about 0.7% of the original mass of the 4 hydrogen nuclei. But when you're converting 620 million tons of hydrogen into helium every single second, as our sun does, that small percentage adds up to those 4 million tons of mass transformed into energy that we talked about. It's like the universe has an exchange rate between matter and energy, and the sun is constantly making withdrawals from its matter account to deposit into its energy account, and we're all beneficiaries of this cosmic transaction. The process itself happens in steps, not all at once, and there's something almost musical about the way it unfolds. First, 2 protons come together, and in that meeting one of them transforms into a neutron through a process called beta decay, releasing a positron and a neutrino. This creates something called a deuterium nucleus, heavy hydrogen. This first step is actually the slowest part of the whole process, the rate-limiting step, as chemists would say. It's so slow that on average, a proton in the sun's core will bounce around for billions of years before it successfully completes this first step. But the sun's core contains so many protons that even this slow process happens countless times every second. Once that deuterium nucleus exists, things speed up a bit. Another proton comes along and fuses with the deuterium to create a light isotope of helium, helium-3, releasing a gamma ray in the process. Then 2 of these helium-3 nuclei find each other and fuse, creating regular helium-4 and releasing 2 protons back into the mix to start the cycle again. It's like a cosmic recycling program, where the raw materials keep getting reused while energy flows outward. This whole sequence is called the proton-proton chain, and it's the dominant fusion process in stars like our Sun. Larger, hotter stars use a different process called the CNO cycle, but our Sun, in its middle-aged stability, prefers the steady, patient proton-proton chain. What moves me about this process is its profound patience. That gamma ray released in the fusion process, that pure electromagnetic energy, doesn't immediately zip out to space. Instead, it begins an incredible journey that will take anywhere from 10,000 to 170,000 years just to travel from the core to the sun's surface. The interior of the sun is so dense that this light bounces from particle to particle, absorbed and re-emitted countless times, slowly random walking its way outward. By the time it finally emerges from the sun's surface, what started as a gamma ray has been broken down into thousands of visible light photons, infrared photons, and other forms of electromagnetic radiation. It's like the universe takes this concentrated energy and dilutes it, makes it gentler, more suitable for nurturing life rather than destroying it. As you lie there listening, perhaps you can feel some of that ancient light on your skin, even if it's nighttime where you are. The warmth stored in your walls, in your blankets, in the very air around you, all of it traceable back to fusion reactions that happened in the sun's core when our ancestors were just beginning to tell stories around fires. There's a continuity here that connects us across impossible spans of time. The warmth you feel is a message from the deep past, carried by light that has been travelling and transforming for eons before it reached you. Now, as we settle deeper into this contemplation, I'd like to share something that might help you appreciate the true scale of what we're discussing. If you were to take all the energy the sun produces in just 1 second, all that transformed mass becoming light and heat and radiation, it would be enough to power our entire human civilization, with all our cities and industries and technologies, for about 500,000 years. And yet the sun does this every second, has been doing it every second for billions of years, will continue doing it every second for billions more. We're talking about a level of consistency and power that makes every human achievement seem like a brief flicker, and yet it happens so quietly, so steadily, that we barely notice it except to comment on whether it's a nice day outside. The neutrinos I mentioned earlier, those ghostly particles released in the fusion process, they tell us another part of this story. Unlike the light that takes millennia to escape the sun's dense interior, neutrinos barely interact with matter at all. They zip straight out from the core at nearly the speed of light, passing through the sun's entire bulk as if it weren't there. 8 minutes later, they're passing through Earth, through you, through me. In fact, about 100 trillion solar neutrinos pass through your body every second, day and night, whether the sun is above or below the horizon. You don't feel them because they're so reluctant to interact with ordinary matter that you'd need a wall of lead about a light year thick to have a 50-50 chance of stopping just one of them. These neutrinos carry information directly from the sun's core, a real-time update on the fusion processes happening right now. When scientists first started detecting solar neutrinos in the 1960s, they found only about a third of what they expected, leading to what was called the solar neutrino problem. It took decades to solve this puzzle, and the solution revealed something beautiful about the nature of these particles. They oscillate between different types as they travel, a quantum mechanical dance that speaks to the fundamental interconnectedness of matter and energy. The scientist who figured this out won the Nobel Prize, but what strikes me is how this discovery came from paying attention to something most of us never notice. These invisible messengers passing through us constantly, carrying news from the heart of our star. There's something profoundly peaceful about knowing that this process, this gentle loss of mass, this transformation of matter into energy, requires no intervention from us, no management, no concern. The sun doesn't need us to tend it or worry about it. It simply continues its patient work, this stellar metabolism that has been the one constant throughout all of Earth's history. When the first life forms emerged in the primordial oceans, the sun was doing this. When dinosaurs walked the Earth, the sun was doing this. When humans first looked up and wondered what that bright disk might be, the sun was doing this. And long after our species has passed into memory, the sun will still be doing this, still converting mass to energy, still losing those 4 million tons per second in the most productive loss imaginable. I find it helps to think of the sun not as losing mass, but as spending it, investing it in the continuation of everything we know. Every photon that warms a rock, every bit of light that triggers photosynthesis in a leaf, every ray that evaporates water to form clouds, all of these are purchases made with solar mass, transactions in the economy of existence. The sun is quite literally spending itself to keep the solar system alive and dynamic, and it has such vast reserves that it can afford to be generous on a scale we can barely comprehend. The sun contains about 330,000 times the mass of Earth, and even losing 4 million tons per second, it would take about 14 trillion years to completely exhaust its mass through this process. Far longer than the sun will actually exist, since other processes will transform it long before then. As we continue our gentle exploration, perhaps you're wondering how we even know all of this. How can we possibly measure something like the sun losing mass? We can't put it on a scale after all. The answer lies in the convergence of many different types of observations, each one adding a piece to our understanding. We measure the total amount of sunlight reaching Earth using satellites like SOURCE and TSIS-1, instruments so sensitive they can detect changes in solar output of just 0.01%. We know how much energy each fusion reaction releases from laboratory experiments and theoretical calculations that have been refined over decades. We can count those ghostly neutrinos using vast underground detectors filled with pure water or exotic liquids, confirming that fusion is indeed happening at the predicted rate. We also listen to the sun itself. Yes, the sun makes sound, not sound that can travel through the vacuum of space, but acoustic waves that bounce around inside the sun, causing its surface to rise and fall by tiny amounts, just a few meters, with periods ranging from minutes to hours. By carefully watching these oscillations using networks of telescopes like GONG and space-based observatories like SOHO and SDO, scientists can probe the Sun's interior, much like geologists use seismic waves to study Earth's interior. This field, called helioseismology, has revealed the rotation rates of different layers within the Sun, the depth of the convection zone, and confirmed our models of the Sun's structure with remarkable precision. It's like the Sun is constantly humming, and by listening carefully to its song, we can understand what's happening in places we could never directly observe. The solar wind adds another dimension to our story of mass loss. Beyond the transformation of mass into energy through fusion, the Sun also loses mass in a more conventional way. It's evaporating, slowly but steadily, sending streams of charged particles out into space. This solar wind, discovered in the 1950s and studied by a flotilla of spacecraft over the decades, carries away about 1 million tons of the Sun's mass every second. So in addition to those 4 million tons converted to energy, there's another million tons actually leaving as particles. These particles stream outward at speeds ranging from 300 to 800 kilometers per second, creating a vast bubble around our solar system called the heliosphere. The solar wind isn't uniform. It has fast streams and slow streams, dense regions and thin regions, all shaped by the Sun's complex magnetic field. When these particles reach Earth, they interact with our planet's magnetic field, creating the aurora borealis and aurora australis, those shimmering curtains of light that dance across polar skies. Every aurora is, in a sense, a visible sign of the Sun's mass loss, a gentle reminder that our star is slowly dispersing itself into the cosmos. But don't worry, even combining the mass loss to fusion and the solar wind, the Sun has only lost about 0.05% of its mass over its entire 4.6 billion year lifetime. At this rate, it would take 100 billion years to lose just 5% of its mass, and the Sun will evolve into a red giant and then a white dwarf long before such losses could significantly affect it. The Parker Solar Probe, launched in 2018, is right now flying closer to the Sun than any spacecraft before it, actually passing through the solar corona, that incredibly hot outer atmosphere where the solar wind is born. It's sampling the solar wind at its source, helping us understand how particles get accelerated to such high speeds, how the corona can be hundreds of times hotter than the Sun's surface. Another mystery we're still working to fully understand. Every bit of data from Parker is helping us refine our picture of how the Sun loses mass, how it breathes out this constant stream of particles that fills the solar system. There's something deeply moving about the fact that we're made of star stuff, as Carl Sagan famously said, but it goes even deeper than that. We're not just made of material that was once inside stars, we're constantly receiving transformed star material in the form of energy. Every calorie of food you've ever eaten ultimately came from sunlight captured by plants. Every movement you make is powered by energy that was once mass in the Sun's core. In a very real sense, you're animated by transformed solar mass. The Sun is becoming part of you, not just historically, but continuously, moment by moment, breath by breath. As you lie there in the darkness, or perhaps in the gentle light of day, consider that the warmth you feel, the light you see, even the food you ate for dinner, all of it represents mass that the Sun has sacrificed, transformed, given away. And it does this with no thought of return, no expectation of gratitude, just the patient continuity of nuclear fusion proceeding according to the laws of physics. There's something almost Zen-like about it. This acceptance of loss that is actually a form of giving, this decrease that enables all increase elsewhere. The mass-energy equivalence that Einstein discovered reveals something profound about the nature of reality, that matter and energy are not separate things, but different faces of the same fundamental essence. The Sun is constantly demonstrating this equivalence, showing us that what seems solid and permanent can become light and movement, that mass can become the warmth in a child's smile, the green of a leaf, the blue of the ocean. It's alchemy of the highest order, not turning lead into gold, but turning hydrogen into helium and liberating the light that makes everything else possible. When we measure the Sun's mass loss, we're really measuring the rate at which our star is powering the solar system. Those 4 million tons per second represent the fuel consumption of our local star engine, the metabolic rate of our stellar parent. and like any engine, like any metabolism, it speaks to both continuity and change, both stability and transformation. The sun is stable because it's changing, maintains its equilibrium through this constant conversion. If the fusion were to suddenly stop, the sun would begin to collapse under its own gravity within minutes. It's the outward pressure of all that fusion energy that holds the sun up against its own weight, a balance that has persisted for billions of years. This balance is so precise, so self-regulating, that it's worth pausing to appreciate. If the sun's core gets slightly hotter, fusion speeds up, producing more energy, which causes the core to expand and cool, which slows fusion back down. If it gets cooler, the opposite happens. Gravity compresses it more, heating it up, increasing the fusion rate. It's a natural thermostat that has kept the sun's energy output remarkably stable over geological time. This stability, born from the feedback between gravity and fusion, between mass and energy, is what has allowed life on Earth to evolve and flourish. We exist in the sweet spot made possible by the sun's patient, self-regulating consumption of its own mass. I want to share something that might help you visualize this process in a different way. Imagine if you could see the sun not as we normally do, as a bright disk in the sky, but as a time-lapse spanning millions of years. You would see it slowly breathing, its surface rising and falling with convection currents that bring heat from the interior. You would see sunspots appear and disappear in 11-year cycles, magnetic field lines twisting and snapping, occasionally launching coronal mass ejections that send billions of tons of solar material racing through space. And underlying all of this activity, you would sense the steady pulse of fusion in the core, the heartbeat of our star, consuming mass to produce energy with a patience that human minds struggle to comprehend. The discovery that the sun loses mass was not a single eureka moment, but a gradual realization that emerged from centuries of scientific progress. Ancient astronomers tracked the sun's movement and noticed its constancy. Medieval scholars preserved and translated this knowledge. Renaissance scientists began to measure solar properties more precisely. The discovery of radioactivity in the late 1800s hinted that there might be energy sources beyond chemical burning. Einstein's special relativity in 1905 revealed the mass-energy relationship. Hans Bether's work in the 1930s detailed the fusion processes. The detection of solar neutrinos in the 1960s confirmed fusion was happening. Modern satellites and telescopes have refined our measurements to extraordinary precision, each generation built on the last, approaching closer to understanding this gentle loss that powers our world. It strikes me that we live in the first era of human history, where we can actually detect and measure the sun's mass loss in real time. Your great-grandparents might have wondered what powered the sun, but they couldn't know. Your grandparents might have learned about nuclear fusion in school, but they couldn't detect the neutrinos. Your parents saw the first detailed images of the solar surface, but they didn't have the precision instruments we have today. You, listening right now, are part of the first generations of humans who can track the sun's mass loss with such accuracy that we can predict how it will affect planetary orbits over millions of years. We're witnesses to a process that has been happening since before Earth existed, but only now can we truly see it, measure it, understand it. The implications ripple outward in ways both practical and profound. On the practical side, understanding solar mass loss helps us predict space weather, protecting satellites and astronauts from solar storms. It helps us understand how the solar system will evolve over geological time, how Earth's orbit will slowly spiral outward as the sun loses mass and its gravitational grip weakens. It provides a baseline for understanding other stars, for searching for potentially habitable planets around them, for comprehending the life cycles of stellar systems throughout the universe. On the profound side, it connects us to the cosmos in an intimate way. We're not separate from the universe watching it from outside. We're part of the process, participants in the transformation. The sunlight that warms your face is mass that has become energy. The food you eat is sunlight captured and stored by plants. The fossil fuels we burn are ancient sunlight, solar energy captured millions of years ago. Even the tides, primarily driven by the moon's gravity, are subtly influenced by solar heating of the oceans. Everything is connected, everything is in flux, everything is participating in this slow, patient transformation of matter into energy, of potential into actual, of being into becoming. As we approach the deeper layers of this mystery, I want to acknowledge something that might be occurring to you. This all sounds rather abstract, these millions of tons, these fusion processes, these vast timescales. But here's what makes it real and immediate. Every second of your life has been lived in the light of this process. Every memory you have was formed in a brain powered by transformed solar mass. Every person you've ever loved, you've seen them by sunlight or by artificial light powered ultimately by the sun. Every book you've read, every sunset you've watched, every meal you've enjoyed, all of it has been made possible by the sun's patient conversion of mass into energy. There's no separation between the cosmic and the personal here. The sun's mass loss is not some distant astronomical phenomenon. It's the most intimate process imaginable, literally enlightening every moment of your existence. When physicists calculate that the sun loses 4 million tons of mass every second, they're calculating the fuel consumption rate of your life, of all life, of everything that happens in our solar system that requires energy. It's the cosmic accounting that underlies every small joy and great achievement, every quiet moment and grand adventure. Let me paint you another picture, this one more intimate. Right now, as you listen to my voice, whether you're in bed preparing for sleep, sitting in a comfortable chair, or perhaps going about some quiet evening task, you're surrounded by the evidence of the sun's mass loss. The warmth in your room, even if it's heated by electricity or gas, ultimately traces back to solar energy. Either recent sunlight that grew the trees that became firewood, ancient sunlight that became fossil fuels, or current sunlight generating electricity through solar panels or driving the weather systems that power wind turbines and hydroelectric dams. The light by which you see, whether it's daylight or electric light, represents transformed solar mass. Even the chemical energy in your body, the ATP molecules that power every cell, every thought, every heartbeat, all of it derives from sunlight captured by plants and passed up the food chain to you. You are, in a very real sense, a temporary arrangement of matter and energy that exists only because the sun is willing to lose mass. Your consciousness, your awareness of existing, your ability to wonder about these very questions, all of it is powered by the sun's patient sacrifice, and not just powered in some abstract sense, but literally made possible by the energy flowing from fusion reactions happening right now, at this very moment, in the sun's core. Those reactions are producing the neutrinos passing through you right now, the light that will reach Earth in 8 minutes, the warmth that will drive tomorrow's weather. When we talk about the sun losing 4 million tons of mass every second, we're really talking about the rate at which possibility becomes actuality, the rate at which the potential energy locked in matter becomes the kinetic energy of life and movement and change. It's a transformation so fundamental that without it, the universe would be static, cold, and lifeless. But with it, we get this extraordinary cosmos full of movement and warmth, and the possibility of consciousness contemplating its own existence. The gentleness of this process is what strikes me most deeply. The sun doesn't explode all its fusion energy at once. That would be a supernova, and we wouldn't be here to discuss it. Instead, it parcels out its energy over billions of years, a slow burn that provides just enough warmth to keep Earth's oceans liquid, just enough light to power photosynthesis, just enough stability to allow evolution to work its patient magic. The sun's mass loss is calibrated by the laws of physics and the balance of forces to be exactly what's needed to sustain a living world. Consider how different things would be if the rate were different. If the sun lost mass faster, converting say 40 million tons per second instead of 4 million, it would be 10 times brighter, and Earth would be a scorched, lifeless rock. If it lost mass slower, converting only 400,000 tons per second, Earth would be frozen solid, its oceans locked in ice. The actual rate, those 4 million tons per second, sits in a sweet spot that allows for liquid water, moderate temperatures, and the complex chemistry of life. It's not that the universe was designed for us. Rather, we evolved to fit the universe as it is. And the universe as it is includes stars that lose mass at just the right rate to create habitable zones around them. This brings us to a deeper contemplation about time and change. The sun's mass loss reminds us that nothing in the universe is permanent, that everything is in process, everything is becoming something else. But it also shows us that change can be so slow, so steady, that it provides a kind of functional permanence, a stability that emerges from constant transformation. The Sun has been losing mass for billions of years, will continue losing mass for billions more, and yet from our human perspective, it might as well be eternal. Our entire species, our entire civilization, exists within what is essentially a single moment of the Sun's life, a brief interval during which the Sun appears unchanging even as it constantly changes. There's a profound lesson here about the nature of existence itself. We often think of things as either permanent or impermanent, stable or unstable, but the Sun shows us a third way, a dynamic equilibrium that is both constant and changing, both stable and transforming. It's losing mass every second, and yet it remains the Sun. It's consuming itself, and yet it persists. It's dying very slowly, and yet it's fully alive, fully functional, fully generous with its energy. As you drift towards sleep tonight, perhaps you can hold this paradox gently in your mind. The Sun that seems so permanent is constantly changing, constantly losing mass, constantly transforming matter into energy. And this very process, this gentle loss, is what makes everything else possible. Every star you see in the night sky is doing something similar, converting mass to energy, slowly spending themselves to light up the darkness. The entire visible universe is engaged in this patient alchemy, this transformation of matter into light, and we are here to witness it, to be part of it, to be illuminated by it both literally and figuratively. The mathematics of it all has an almost musical quality when you think about it. 4 million tons per second. It's like a cosmic metronome, keeping time for the solar system. Each second, tick, 4 million tons becomes energy. Tick, another 4 million tons. Tick, 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 with a regularity that has persisted since before Earth formed and will continue long after we're gone. It's the baseline rhythm of our local cosmos, the drumbeat to which all solar system processes dance. Planetary orbits, asteroid trajectories, comet paths, the solar wind, magnetic fields, aurora displays, all of them move to this fundamental rhythm of mass becoming energy at 4 million tons per second. And yet, despite this enormous number, despite the scale that defies human comprehension, the process is so smooth, so quiet, that if you didn't know to look for it, you'd never notice. The Sun rises and sets, the seasons change, years pass, and nothing seems different. It takes precise scientific instruments to detect the tiny changes in solar output, the subtle variations in the solar wind, the minute alterations in planetary orbits that result from the Sun's mass loss. Nature operates on scales both vast and minute, and the Sun's mass loss occupies a special place where enormous absolute numbers translate into tiny relative changes, where millions of tons per second amounts to a loss so gradual it's essentially imperceptible on human timescales. This hidden grandeur, this invisible magnificence surrounds us always. We live our entire lives bathed in the product of the Sun's mass loss, without ever feeling the loss itself. It's like living downstream from a vast dam that releases water so steadily you'd never know the reservoir was slowly dropping, unless you had instruments to measure it. The energy flows to us, through us, around us, sustaining everything we know, and the source depletes itself so slowly that for all practical purposes, it might as well be infinite. But knowing about this process, understanding even a little bit about what's happening, adds a dimension of depth to everyday experience. When you feel sunlight on your skin tomorrow, you might remember that you're feeling mass that has become energy. When you see shadows dancing as clouds pass overhead, you might think about the 8-minute journey that light took to reach us from the Sun. When you eat your next meal, you might consider that you're consuming captured sunlight, stored solar energy, transformed stellar mass. This knowledge doesn't change the experience, but it can deepen it, add layers of meaning and connection that weren't there before. The story of discovering the Sun's mass loss is also a story about human curiosity and ingenuity. No one person figured this out alone. It took centuries of accumulated knowledge, thousands of scientists working on different pieces of the puzzle, often not knowing how their work would fit into the larger picture. The astronomers who first accurately measured the distance to the Sun didn't know their work would be crucial for calculating solar luminosity. The physicists who worked out the details of nuclear fusion didn't know their equations would explain how stars shine. The engineers who built neutrino detectors didn't know their machines would confirm processes happening in the sun's core. Each contribution built on what came before, and together they revealed this extraordinary truth about our star's gentle self-consumption. Today we have spacecraft orbiting the sun, flying through the solar wind, measuring magnetic fields, counting particles, analysing light across the electromagnetic spectrum. We have telescopes on Earth, and in space watching the sun 24 hours a day, tracking every sunspot, every flare, every subtle change in output. We have underground laboratories detecting neutrinos, confirming that fusion is happening at the predicted rate. We have supercomputers modelling the sun's interior, simulating the complex magnetohydrodynamics of stellar plasma. All of this effort, all of this technology, all of this human ingenuity, devoted to understanding a process that happens whether we understand it or not. The sun losing 4 million tons of mass every second, transforming matter into energy, powering the solar system, enabling life. There's something beautiful about the fact that we've reached a point in our development as a species where we can understand the very process that makes our existence possible. We're like children who have finally grown up enough to understand how our home works, how the lights stay on, how the heat flows through the pipes. But instead of pipes and wires, we're talking about fusion reactions and solar wind. Instead of monthly utility bills, we're talking about mass energy conversion at millions of tons per second. The scale is cosmic, but the impulse is the same: to understand our home, to comprehend the systems that sustain us, and what a home it is. The solar system, powered by the sun's mass loss, is a dynamic, ever-changing environment. Planets orbit in their stately paths, but those paths are slowly expanding as the sun loses mass and its gravity weakens. Asteroids tumble through space, their surfaces alternately baking in sunlight and freezing in shadow. Comets swing in from the outer darkness, their ices sublimating in the sun's warmth, creating those spectacular tales that have awed humans throughout history. The solar wind blows outward, creating a vast bubble called the heliosphere that protects us from the harsher radiation of interstellar space. All of this activity, all of this motion and change, powered by the sun's patient conversion of mass into energy. When we detect exoplanets around other stars, we're seeing other systems where similar processes are playing out, each star losing mass at its own rate, each one converting hydrogen to helium or heavier elements, each one broadcasting energy into space. Some lose mass faster than our sun, burning bright and dying young. Others lose mass much more slowly, dim red dwarfs that will shine for trillions of years. But all of them are doing essentially what our sun does, transforming matter into energy, spending themselves to light up the darkness, creating zones of warmth and possibility in the cold vastness of space. This universality of stellar mass loss connects us to the cosmos in a profound way. The same process happening in our sun is happening in billions upon billions of other stars throughout the universe. We're part of a vast community of stellar systems, all powered by the same fundamental physics, all participating in the same cosmic transformation of matter into energy. When you look at the night sky, every star you see is losing mass, converting matter into the light that reaches your eyes. The entire visible universe is engaged in this process, this gentle burning that makes everything else possible. As we move deeper into our contemplation, approaching the intricate mechanisms behind this mass loss, I want to pause and acknowledge the profound peace that comes from understanding these processes. There's something deeply calming about knowing that the sun's mass loss is not a crisis, not a problem to be solved, not a threat to be worried about. It's simply how stars work, how they've always worked, how they'll continue to work long after our species has passed into history. This knowledge can free us from a certain kind of cosmic anxiety, the worry that things might suddenly change, that the lights might go out, that the warmth might cease. The sun will continue its patient transformation for billions of years to come, far longer than any timescale relevant to human concerns, E=mc². Such a simple equation, just 5 characters including the equal sign, and yet it describes one of the most profound relationships in nature. Energy equals mass times the speed of light squared. When Einstein first wrote this down in 1905, he couldn't have imagined all the ways it would reshape our understanding of the universe. He was thinking about the relationship between matter and energy in abstract terms, working out the consequences of his special theory of relativity. But this equation would go on to explain how stars shine, how nuclear weapons work, how particle accelerators create new forms of matter, how the entire universe is engaged in a constant dance of transformation between matter and energy. In the Sun's core, E equals m squared is not just an equation, it's a recipe, a formula for transformation being followed billions of times every second. Each time 4 hydrogen nuclei combine to form helium, a tiny bit of mass disappears and becomes energy according to this equation. The speed of light, c, is such a large number, 300,000 kilometers per second, that when you square it, you get an enormous conversion factor. This means that even a tiny amount of mass can become a tremendous amount of energy. 1 kilogram of matter, if completely converted to energy, would release about 90 petajoules of energy, equivalent to about 21 megatons of TNT, or enough to power a large city for years. But the Sun doesn't convert matter to energy with perfect efficiency. In the proton-proton chain, only about 0.7% of the mass actually becomes energy. The rest remains as matter, just rearranged into helium instead of hydrogen. Even so, this 0.7% efficiency, applied to the 620 million tons of hydrogen the Sun fuses every second, yields those 4 million tons of mass converted to pure energy. It's like a cosmic tax on fusion. For every 100 pounds of hydrogen that fuse, about 11 ounces become energy while the rest becomes helium. This might seem inefficient, but it's actually perfect for our needs. If the conversion were more efficient, stars would burn out much faster. If it were less efficient, they might not shine brightly enough to warm planets. The energy released in each individual fusion reaction is tiny, just a few million electron volts, an amount so small that it would take trillions upon trillions of such reactions to power a single light bulb for a second. But the Sun's core is vast, containing about 1057 protons, and the conditions there are so extreme that fusion reactions are happening constantly throughout a region larger than Jupiter. The cumulative effect of all these tiny reactions is the Sun's total luminosity, about 384 yottawatts, or 384 trillion watts. That's more power than humanity has generated in its entire history being released every nanosecond. To help put this in perspective, let's think about the journey of a single fusion reaction's energy. Deep in the core, 4 protons come together through a series of interactions and create one helium nucleus, releasing energy in the form of gamma rays and neutrinos. The neutrinos, as we discussed, zip straight out of the Sun at nearly the speed of light. But the gamma rays begin an incredible journey that will take them anywhere from 10,000 to 170,000 years just to reach the Sun's surface. This journey is so long and tortuous because the Sun's interior is incredibly opaque to radiation. A gamma ray can only travel about a millimeter before being absorbed by a particle, which then re-emits the energy, often at a lower frequency and in a random direction. This process, called radiative diffusion, is like trying to cross a crowded room where every step you take, someone spins you around and points you in a new direction. The gamma ray's energy random walks its way outward, bouncing from particle to particle billions upon billions of times. As it travels outward and the temperature drops, the energy gets divided among more and more photons. What started as a single high-energy gamma ray eventually becomes thousands of visible light photons, infrared photons, and other forms of electromagnetic radiation. About 70% of the way from the center to the surface, the temperature drops enough that convection becomes more efficient than radiation for transporting energy. Here, in the convection zone, vast cells of hot plasma rise to the surface, cool and sink back down like water boiling in a pot but on a stellar scale. These convection cells are enormous, some are larger than Earth, and they carry energy from the radiative zone to the photosphere, the visible surface of the Sun, in a matter of weeks rather than millennia. When the energy finally reaches the photosphere, it's released into space as sunlight, the light we see, the warmth we feel, the energy that powers our world. The photosphere is relatively cool compared to the core, only about 5800 Kelvin, which is why the Sun appears yellow-white rather than blue or violet. If we could see the Sun's core directly, it would be emitting primarily in the X-ray and gamma ray portion of the spectrum. But by the time that energy reaches the surface, it's been thermalized, spread out across the electromagnetic spectrum in a way that's remarkably beneficial for life on Earth. The spectrum of sunlight that reaches Earth peaks in the visible range, right where our eyes are most sensitive. This is no coincidence. We evolved under this sun, and our vision adapted to make the best use of the available light. But the sun also emits infrared radiation that warms us, ultraviolet radiation that drives vitamin D production in our skin, while too much can cause sunburn, and small amounts of radio waves, microwaves, X-rays, and other forms of electromagnetic radiation. All of this energy across the entire spectrum originated as mass in the sun's core that was converted to energy through fusion. The constancy of this process is remarkable. The sun's energy output varies by only about 0.1% over the course of the 11-year solar cycle, and even smaller variations occur on shorter timescales. This stability is crucial for life on Earth. If the sun's output varied significantly, our climate would swing wildly between too hot and too cold for complex life to survive. But the sun's mass loss through fusion is so steady, the process so well regulated by the balance between gravity and radiation pressure, that we can count on consistent sunlight from day to day, year to year, century to century. This brings us to one of the most profound aspects of stellar mass loss. It's self-regulating. If the sun's core were to somehow get hotter and fusion were to speed up, the extra energy would cause the core to expand, which would cool it down and slow fusion back to normal. If the core were to cool and fusion were to slow, gravity would compress it, heating it back up and returning fusion to its normal rate. This negative feedback loop has kept the sun stable for billions of years and will continue to do so for billions more. It's like a thermostat that requires no external control, no maintenance, no adjustment, just the natural interplay of fundamental forces. The proton-proton chain that powers our sun is just one of several fusion processes that stars can use to convert mass to energy. Larger, hotter stars primarily use the CNO cycle, where carbon, nitrogen and oxygen act as catalysts to fuse hydrogen into helium. Even larger stars can fuse helium into carbon, carbon into oxygen, and so on up to iron. Each of these processes converts a small fraction of mass into energy, following Einstein's equation. The most massive stars in their final moments can even fuse iron, though this actually absorbs energy rather than releasing it, leading to the star's collapse and eventual supernova explosion. Our sun, however, is not massive enough for these more exotic fusion processes. It will spend about 90% of its life fusing hydrogen into helium through the proton-proton chain, slowly and steadily converting 4 million tons of mass into energy every second. This phase, called the main sequence, is the most stable period in a star's life. We're currently about 4.6 billion years into our sun's main sequence phase, with roughly another 5 billion years to go before things start to change significantly. When I think about these timescales, I'm struck by how they dwarf human experience, while simultaneously enabling it. The sun has been losing mass at roughly the same rate since before Earth formed. It was losing 4 million tons per second when the first life emerged in the primordial oceans. It was losing 4 million tons per second when plants first colonized land. It was losing 4 million tons per second when dinosaurs ruled the Earth, when mammals emerged, when humans first walked upright, when we developed language, agriculture, civilization. Every moment of Earth's history, every evolutionary innovation, every extinction and recovery, has played out against the backdrop of the sun's steady mass loss. And here's something that might give you a sense of cosmic perspective as you drift towards sleep. The sunlight that warmed the dinosaurs was produced by the same process that produces the sunlight warming you right now. The fusion reactions in the sun's core, the conversion of mass to energy, the slow journey of that energy to the surface, it's all the same process, unchanged over hundreds of millions of years. When a T-Rex basked in the Cretaceous sun, it was warmed by hydrogen fusing into helium, by mass becoming energy at 4 million tons per second, just as you are warmed by that same process today. The neutrinos from the sun's core provide us with a real-time window into this process. Unlike light, which takes millennia to escape the sun's dense interior, neutrinos barely interact with matter and stream out immediately. About 65 billion solar neutrinos pass through every square centimetre of Earth's surface every second, and that includes the nighttime side, as neutrinos pass through our entire planet as easily as light passes through glass. As you lie there, roughly 100 trillion solar neutrinos are passing through your body every second, carrying direct information from fusion reactions that happened just 8 minutes ago in the Sun's core. Detecting these neutrinos has been one of the great triumphs of experimental physics. The first successful detection was made in the 1960s by Ray Davis Jr., using a tank of cleaning fluid deep in a gold mine in South Dakota. The chlorine in the cleaning fluid would occasionally interact with a neutrino, converting to argon, which Davis could detect. But the interaction rate was so low that in a tank containing 100,000 gallons of cleaning fluid, only about one neutrino interaction occurred every 2 days. For this painstaking work, which confirmed that the Sun is indeed powered by fusion, Davis shared the 2002 Nobel Prize in Physics. Modern neutrino detectors are even more sophisticated. The Super Kamiokande detector in Japan uses 50,000 tons of ultra-pure water surrounded by thousands of photomultiplier tubes to detect the tiny flashes of light produced when a neutrino interacts with a water molecule. The Sudbury Neutrino Observatory in Canada used heavy water where the hydrogen is replaced with deuterium, to detect neutrinos through multiple interaction channels. These experiments not only confirmed the rate of fusion in the Sun's core, but also solved the long-standing solar neutrino problem by discovering that neutrinos oscillate between different types as they travel from the Sun to Earth. The solar neutrino problem was a beautiful example of how a discrepancy between theory and observation can lead to new physics. For decades, experiments detected only about a third of the neutrinos that theories predicted the Sun should produce. Some scientists wondered if our models of the Sun's interior were wrong, if perhaps the core was cooler than we thought or fusion was proceeding differently. But it turned out the Sun was fine. It was our understanding of neutrinos that needed updating. Neutrinos come in 3 types, or flavors, and they can transform from one type to another as they travel. The early detectors could only see one type, so they missed the 2/3 that had transformed into other flavors during their journey from the Sun. This discovery, confirmed by multiple experiments and honored with the 2015 Nobel Prize in Physics, showed us that neutrinos have mass, tiny mass, but not zero. This was a surprise, as the standard model of particle physics had assumed neutrinos were massless. The fact that they have mass, even though it's less than a millionth the mass of an electron, has profound implications for cosmology and our understanding of the universe. And we learned all this from studying the Sun's mass loss, from trying to understand how 4 million tons per second becomes energy in neutrinos. The precision with which we can now measure the Sun's mass loss is extraordinary. Satellites like SOHO, the Solar and Heliospheric Observatory, have been watching the Sun continuously for decades, measuring its output across the electromagnetic spectrum. The Solar Dynamics Observatory takes high-resolution images of the Sun every 12 seconds in multiple wavelengths, allowing us to see the roiling convection cells on its surface, the twisted magnetic field lines in its corona, the explosive flares that occasionally erupt. The stereo mission used 2 spacecraft to create 3-dimensional images of the Sun, giving us an unprecedented view of coronal mass ejections and the solar wind. All of these observations confirm and refine our understanding of the Sun's mass loss. We can see the convection cells that carry energy from the interior to the surface. We can measure the solar wind streaming outward at hundreds of kilometers per second. We can detect the electromagnetic radiation across all wavelengths and calculate exactly how much energy the Sun is emitting. And it all adds up to those 4 million tons of mass converted to energy every second, plus about another million tons lost as solar wind particles. The solar wind itself is a fascinating aspect of the Sun's mass loss. Unlike the mass converted to energy through fusion, the solar wind represents actual particles, mostly protons and electrons, streaming away from the Sun. This wind varies in intensity and speed, creating a complex and dynamic environment throughout the solar system. The slow solar wind, travelling at about 400 kilometers per second, seems to originate from the Sun's equatorial regions. The fast solar wind, reaching speeds of 750 kilometers per second or more, comes from coronal holes, regions where the Sun's magnetic field lines open out into space rather than looping back to the surface. When this solar wind reaches Earth, it interacts with our planet's magnetic field in complex and beautiful ways. Most of the particles are deflected around Earth, but some spiral down along magnetic field lines near the poles, colliding with atmospheric gases to create the aurora. Every shimmering curtain of green and red light in the polar skies is a visible manifestation of the sun's mass loss, a gentle reminder that we're connected to our star not just by light and heat, but by actual particles that have travelled across 150 million kilometres of space. The Parker Solar Probe, humanity's first mission to touch the sun, is revolutionising our understanding of how the solar wind forms and accelerates. Launched in 2018, it's gradually spiralling closer to the sun, eventually passing within 6 million kilometres of the surface, 7 times closer than any previous spacecraft. At its closest approach, Parker experiences temperatures of nearly 1,400 degrees Celsius and solar radiation 475 times more intense than what we experience at Earth. Yet its instruments continue to function, protected by a special heat shield, sending back data about the magnetic fields, particles and plasma waves in the sun's corona. One of Parker's most surprising discoveries has been the detection of switchbacks in the solar wind, sudden reversals in the magnetic field that cause the solar wind to briefly flow backward toward the sun before resuming its outward journey. These switchbacks might help explain how the solar wind gets accelerated to such high speeds, a mystery that has puzzled scientists for decades. Every piece of data from Parker helps us better understand not just our sun's mass loss, but the fundamental processes that govern all stars. As we contemplate these vast scales and precise measurements, it's worth remembering that all of this knowledge, all of these discoveries, all of these technological achievements are themselves powered by the sun's mass loss. The scientists who built these instruments, the engineers who designed these spacecraft, the technicians who operate these observatories, all of them are animated by food that grew using sunlight, their brains powered by glucose that ultimately derives from photosynthesis, from the sun's patient conversion of mass into energy. We're using solar energy to study solar energy, using the products of fusion to understand fusion, using our star-powered consciousness to comprehend the star that powers us. There's a beautiful recursiveness to this, a kind of cosmic self-awareness where the universe has evolved parts of itself complex enough to understand the processes that make that complexity possible. Through us, the sun is in a sense studying itself, understanding its own mass loss, comprehending its own transformation of matter into energy. We are the universe's way of knowing itself, and what we're learning is that we exist because stars like our sun are willing to slowly consume themselves to transform their mass into the energy that makes everything else possible. As you continue to relax, perhaps letting your breathing slow to match the patient rhythms of stellar processes, consider how the sun's mass loss connects to everything around you. The warmth of your blanket, the softness of your pillow, the very air you're breathing, all of it exists in its current form because of energy that was once mass in the sun's core. The chemical bonds in every molecule, the thermal motion of every atom, the quantum states of every electron, all of it is influenced by the steady rain of photons from our mass-losing star. Even the passage of time itself is marked by the sun's mass loss. Our days are defined by Earth's rotation relative to the sun. Our years are measured by Earth's orbit around the sun. And both of these are gradually changing as the sun loses mass. Each year is getting about 1.5 microseconds longer, as Earth's orbit slowly expands in response to the sun's decreasing gravity. It's an imperceptibly small change. It would take about 60,000 years for the accumulated effect to add up to a single second, but it's real, measurable, a direct consequence of those 4 million tons per second converted to energy. This connects to a deeper truth about the universe. Everything is in motion, everything is changing, nothing is truly static. Even the things that seem most permanent, the sun, the stars, the galaxies, are all in process, all transforming, all participating in the cosmic dance of matter and energy. The sun's mass loss is just one particularly clear and measurable example of this universal principle. Every atom in your body, every particle in the universe, is constantly changing, constantly interacting, constantly participating in the great transformation that we call existence. And yet within all this change, patterns persist. The laws of physics that govern the sun's mass loss are the same laws that operated billions of years ago and will operate billions of years hence. E=mc² is not subject to fashion or politics or personal preference. It simply describes how the universe works, how mass and energy relate, how stars can shine for billions of years. There's a deep comfort in this constancy within change, this reliability of natural law even as everything it governs is in flux. The sun doesn't just lose mass through fusion in its core, it also breathes out a constant stream of particles into space, a solar wind that carries away about 1 million tons of matter every second. This is actual material, protons and electrons and heavier ions, flowing outward from the sun's corona at speeds that would cross the entire United States in less than 10 seconds. Unlike the 4 million tons converted to energy through fusion, this million tons of solar wind represents a true loss of particles, atoms that once were part of our star now streaming into the vastness of interstellar space, never to return. Picture, if you will, the sun's atmosphere extending far beyond its visible surface, reaching out past Mercury, past Venus, past Earth, past Mars, continuing outward until it meets the interstellar medium somewhere beyond the orbit of Pluto. This extended atmosphere, this sphere of solar influence, is filled with the solar wind, a hot, thin plasma carrying the sun's magnetic field with it as it expands into space. It's as if the sun is gently evaporating, subliming directly from its hot corona into the cold vacuum, creating a bubble of solar material that encompasses our entire planetary system. The discovery of the solar wind is a relatively recent chapter in our understanding of the sun. For centuries, astronomers noticed that comet tails always point away from the sun, regardless of the comet's direction of motion. This was puzzling. If comet tails were simply trailing behind like smoke from a moving train, they should point backward along the comet's path. But they don't. They always point radially outward from the sun, like spokes on a wheel with the sun at the centre. In the 1950s, Eugene Parker proposed a radical explanation. The sun must be emitting a constant stream of particles that pushes comet tails away, like wind blowing a flag. Parker's hypothesis was controversial. Many scientists couldn't believe that the sun's gravity would allow particles to escape continuously. But Parker showed mathematically that the sun's corona is so hot, over 1 million degrees, that not even the sun's enormous gravity can contain it completely. The hot gas must expand outward, accelerating as it goes, reaching supersonic speeds within a few solar radii. This wasn't a gentle evaporation, but a supersonic wind, carrying mass, energy, and magnetic field away from our star at prodigious rates. When the first interplanetary spacecraft confirmed the solar wind's existence in the 1960s, Parker was vindicated, and our understanding of the sun transformed from a distant, isolated star to an active, breathing presence that fills the entire solar system. The solar wind isn't uniform or constant. It has structure, variety, a kind of weather all its own. There's the slow solar wind, emerging from near the sun's equator at speeds of about 400 kilometers per second, dense and variable, carrying about twice as many particles per cubic centimeter as the fast wind. Then there's the fast solar wind, streaming from coronal holes at speeds approaching 800 kilometers per second, thinner but steadier, creating high-speed streams that rotate with the sun like a cosmic sprinkler system. When fast wind catches up to slow wind, it creates compression regions, shock waves, turbulence, a complex pattern of interaction that propagates throughout the solar system. Observations from spacecraft like Ulysses, which flew over the sun's poles, revealed that the solar wind structure changes with the solar cycle. During solar minimum, when the sun's magnetic field is relatively simple and dipolar, the fast wind dominates at high latitudes while slow wind emerges near the equator. During solar maximum, when the magnetic field becomes complex and tangled, slow and fast wind can emerge from any latitude, creating a much more chaotic and variable outflow. It's as if the sun has different breathing patterns depending on its magnetic mood, sometimes steady and regular, sometimes gusty and irregular. The ZOHO spacecraft, positioned at the L1 Lagrange point between Earth and the Sun, has been monitoring the solar wind continuously since 1996. Its instruments measure the wind speed, density, temperature, and composition, providing an early warning system for space weather, while also revealing the fundamental processes that accelerate particles away from the Sun. ZOHO has shown us that the solar wind isn't just hydrogen and helium. It contains traces of heavier elements like carbon, oxygen, and iron. Their abundance ratios providing clues about the temperature and magnetic conditions in the regions where the wind originates. The ACE spacecraft, the Advanced Composition Explorer also stationed at L1, specializes in measuring the elemental and isotopic composition of the solar wind. It has revealed that the wind's composition varies depending on its source region and speed. The slow wind has a composition similar to the Sun's corona, while the fast wind seems to come from deeper, cooler layers. These compositional differences are like fingerprints, allowing scientists to trace different streams of solar wind back to their sources on the Sun, mapping the connection between what we observe at Earth and what's happening at our star. The WIND spacecraft, another Sentinel at L1, focuses on the plasma physics of the solar wind, the complex interactions between particles and magnetic fields that govern how the wind behaves. WIND has discovered that the solar wind is far from the smooth laminar flow that early models predicted. Instead, it's turbulent at all scales, from vast structures millions of kilometers across down to tiny fluctuations at the scale of individual particle interactions. This turbulence isn't just noise, it plays a crucial role in heating the wind, accelerating particles, and determining how the wind interacts with planetary magnetospheres. Consider the journey of a single particle escaping from the Sun as part of the solar wind. It begins in the chromosphere or low corona, held to the Sun by gravity and magnetic fields. But the temperature here is extraordinary, over 1 million degrees in the corona compared to just 6,000 degrees at the visible surface. At these temperatures, particles are moving so fast that some achieve escape velocity. But it's not just thermal motion that allows escape. The magnetic field plays a crucial role, creating channels and pathways that guide particles outward, accelerating them through a process we still don't fully understand. As our particle rises through the corona, it encounters waves and turbulence in the magnetic field. These waves can accelerate particles, like a surfer catching a wave, boosting them to speeds far exceeding what temperature alone would provide. The particle spirals along magnetic field lines, gradually breaking free from closed loops to follow open field lines that extend into interplanetary space. Within a few solar radii, our particle has accelerated to supersonic speeds, joining the stream of solar wind flowing outward through the solar system. The Parker Solar Probe is revolutionizing our understanding of this acceleration process. Flying through the corona itself, Parker is measuring the conditions right where the solar wind is born. It has discovered that the corona isn't a smooth, homogeneous atmosphere, but a highly structured environment with jets, streams, and magnetic switchbacks that might be key to understanding how the wind gets accelerated. Each orbit brings Parker closer to the Sun, deeper into the acceleration region, providing data that no Earth-based telescope or distant spacecraft could obtain. One of Parker's most intriguing discoveries is that the solar wind seems to be accelerated much closer to the Sun than previously thought. Traditional models suggested a gradual acceleration over many solar radii, but Parker is finding evidence for rapid acceleration within just a few solar radii of the surface. This might be due to magnetic reconnection events, where twisted magnetic field lines suddenly snap and reconfigure, releasing energy that accelerates particles. Or it might be due to waves generated by convection at the Sun's surface, propagating upward and depositing their energy in the corona. The truth is, we're still figuring it out, still learning how our star breathes. The IBEX mission, the Interstellar Boundary Explorer, gives us a different perspective on the solar wind by mapping its interaction with the interstellar medium at the very edge of the solar system. IBEX detects energetic neutral atoms created when solar wind particles exchange electrons with interstellar gas, providing images of the heliopause, the boundary where the solar wind finally stops, unable to push any further against the pressure of interstellar space. These images show that the heliosphere isn't spherical as once thought, but has a complex, possibly tail-like shape, sculpted by our motion through the galaxy and the magnetic fields of interstellar space. The Voyager spacecraft, launched in 1977, have actually crossed the heliopause, becoming the first human-made objects to enter interstellar space. Voyager 1 crossed in 2012, Voyager 2 in 2018, and their measurements showed that the boundary isn't a simple, clean edge but a complex region of turbulence and mixing. Even beyond the heliopause, they still detect particles that originated from our Sun, carried outward by the solar wind over years and decades. The Sun's breath extends far beyond what we once imagined, creating a vast bubble of solar influence in the cosmic dark. This bubble, the heliosphere, is our cocoon, our shield against the harsher radiation of interstellar space. Galactic cosmic rays, high-energy particles accelerated by supernovae and other violent cosmic events, are partially deflected by the heliosphere's magnetic field. Without this protection, Earth would be bombarded by far more cosmic radiation, potentially affecting everything from atmospheric chemistry to DNA mutation rates. The solar wind, in its constant outward flow, maintains this protective bubble, another way that the sun's mass loss directly benefits life on Earth. The solar wind also plays a crucial role in planetary evolution throughout the solar system. Mars, with its weak magnetic field, has had much of its atmosphere stripped away by the solar wind over billions of years. The MAVEN spacecraft orbiting Mars has measured this process in real time, watching as solar wind particles collide with the upper atmosphere, giving atmospheric particles enough energy to escape Mars's gravity. What was once a thick atmosphere capable of supporting liquid water on the surface has been gradually eroded away, leaving the thin, dry atmosphere we see today. This is the solar wind as a sculptor, slowly reshaping worlds over geological time. Venus, despite having no magnetic field, has retained its thick atmosphere thanks to its stronger gravity and possibly the induced magnetosphere created by the solar wind's interaction with its ionosphere. But even Venus loses atmosphere to the solar wind, particularly water vapor, which may explain why Venus is so dry compared to Earth. The Venus Express spacecraft measured this atmospheric loss, finding that the solar wind strips away about 100 grams of atmospheric material every second. Tiny compared to the planet's total atmosphere, but significant over billions of years. Earth, protected by its magnetic field, experiences a more complex interaction with the solar wind. Our magnetosphere deflects most of the solar wind around the planet, but some particles spiral down along field lines near the poles, creating the aurora and contributing to atmospheric chemistry. During geomagnetic storms, when the solar wind carries particularly strong magnetic fields, our magnetosphere can be compressed and disturbed, allowing more particles to reach lower altitudes. These storms can affect satellites, power grids, and communication systems, reminders that we live within the sun's extended atmosphere and are subject to its weather. The solar wind carries the sun's magnetic field with it as it flows outward, creating what's called the interplanetary magnetic field. This field spirals outward in a pattern called the Parker spiral, named after Eugene Parker, who first described it. Imagine a garden sprinkler spinning while water flows from its arms. The water traces spiral patterns as the rotation combines with the outward flow. Similarly, the sun's rotation combined with the radial outflow of the solar wind creates magnetic field lines that spiral outward through the solar system. Near Earth, these field lines make an angle of about 45 degrees to the radial direction, becoming more and more wound up at greater distances. This spiraling magnetic field creates sectors in interplanetary space, regions where the field points either toward or away from the sun. Earth passes through these sectors as it orbits, experiencing regular reversals in the interplanetary magnetic field direction. These sector crossings can trigger geomagnetic activity, affecting everything from aurora displays to the radiation environment around Earth. It's as if we're sailing through magnetic weather systems that rotate with the sun, experiencing different conditions depending on which sector we're in. The solar wind's interaction with comets provides some of the most spectacular demonstrations of the sun's extended influence. As a comet approaches the sun, solar radiation heats its icy surface, causing gas and dust to sublime directly into space. The solar wind and radiation pressure then blow this material away from the sun, creating the comet's characteristic tails, actually two tails, one of dust pushed by radiation pressure and one of ionized gas carried by the solar wind's magnetic field. These tails can stretch for millions of kilometers, vast streamers made visible by the sun's breath. The Rosetta mission to Comet 67P Churyumov-Gerasimenko gave us an unprecedented close-up view of this interaction. Rosetta watched as the comet transformed from a relatively quiet, dark object far from the sun to an active, outgassing body as it approached perihelion. The spacecraft measured how the solar wind was deflected around the comet's growing atmosphere, how the comet's own weak magnetic field formed through the interaction with the solar wind, how particles were picked up by the wind and carried away. It was like watching the solar wind sculpt a temporary atmosphere in real time, a process that every comet experiences during its passage through the inner solar system. space weather forecasting has become increasingly important as our technological civilization becomes more dependent on satellites and other space-based infrastructure. Just as meteorologists track hurricanes and cold fronts in Earth's atmosphere, space weather forecasters track coronal mass ejections and high-speed streams in the solar wind. When a coronal mass ejection, billions of tons of solar material expelled in a matter of hours, heads toward Earth, forecasters use models to predict when it will arrive and how strong the geomagnetic storm might be. These predictions help satellite operators, power grid managers, and astronauts prepare for potentially hazardous conditions. The solar wind also affects technological systems in more subtle ways. GPS satellites must account for the drag caused by Earth's atmosphere, which expands and contracts in response to solar wind variations. Satellites in geostationary orbit can accumulate electrical charge from the solar wind, potentially causing damaging discharges. Even pipelines and railway tracks can experience induced currents during geomagnetic storms, leading to increased corrosion or signal disruptions. We've built a technological civilization within the Sun's extended atmosphere, and we must learn to live with its weather. As you contemplate this vast outflow of particles from our star, consider that some of the atoms in the solar wind have been part of the Sun since its formation 4.6 billion years ago. These ancient particles, having spent billions of years in the Sun's convection zone, cycling between the surface and interior, are finally escaping, heading out into interstellar space. Some will be captured by planetary magnetospheres, becoming part of radiation belts or aurora displays. Others will continue outward, eventually crossing the heliopause and mixing with the interstellar medium, perhaps someday to be incorporated into new stars and planets. The solar wind connects us to the cosmos in a very direct way. We're not isolated on Earth, separated from space by an impermeable barrier. Instead, we live within the Sun's atmosphere, constantly touched by particles that were part of our star just days ago. When you see the aurora dancing across polar skies, you're watching the solar wind made visible. When you use GPS to navigate, you're depending on satellites affected by solar wind conditions. When you enjoy a meteor shower, you're seeing debris from comets whose tails were sculpted by the solar wind. We are immersed in our star's breath, participants in a solar system-wide circulation of matter and energy. Recent missions have revealed just how complex and dynamic the solar wind really is. The Solar Orbiter spacecraft, launched in 2020, is using a highly elliptical orbit to study the Sun from different angles and distances, including the first detailed observations of the solar poles. Its instruments can trace solar wind streams back to their sources with unprecedented precision, showing how tiny bright points in the corona, each one about the size of Earth, might be sources of the solar wind. These bright points appear and disappear on timescales of minutes to hours, suggesting that the solar wind source is not steady, but constantly flickering, like countless tiny jets turning on and off. The discovery of the solar wind fundamentally changed our understanding of stellar evolution. We now know that all stars lose mass through stellar winds, and for some stars this wind loss dominates over fusion in determining their evolution. Massive stars can lose more than half their initial mass through powerful winds, dramatically affecting their eventual fate. Red giants shed their outer layers through slow, dense winds, enriching interstellar space with heavy elements. Even tiny red dwarf stars, though their winds are weak, lose mass over their extraordinarily long lifetimes. The solar wind is our local example of a universal process, a window into how stars everywhere breathe out into space. The composition of the solar wind tells us about the Sun's interior in ways that complement what we learn from neutrinos and helioseismology. Different elements are ionized to different degrees in the corona, and these ionization states are frozen into the solar wind as it accelerates outward. By measuring these charged states, we can determine the temperature of the wind's source region. Heavy elements like iron can have many electrons stripped away, requiring temperatures of millions of degrees, while lighter elements show lower ionization states. It's like each particle carries a thermometer reading from its point of origin, allowing us to map temperatures throughout the corona. The solar wind also carries away angular momentum, causing the Sun to gradually spin more slowly over time. Young stars rotate rapidly, sometimes completing a rotation in just a day or two. But as they age and lose mass through stellar winds, they spin down, taking hundreds of millions or billions of years to slow to sedate rotation periods like our Sun's 27 days. This spin-down process affects the star's magnetic field generation, which in turn affects the stellar wind, creating a complex feedback loop that governs stellar evolution. By studying the solar wind, we're learning about processes that affect stars throughout their lifetimes. Coronal mass ejections represent the most dramatic form of solar wind, explosive events where billions of tons of solar material are expelled in a matter of hours. These CMEs, as they're called, can travel at speeds exceeding 3,000 kilometers per second, carrying twisted magnetic fields that can trigger severe geomagnetic storms when they hit Earth. The Halloween storms of 2003, the Carrington event of 1859, the Quebec blackout of 1989, all were caused by CMEs, massive exhalations from our star that temporarily disturbed the usually steady solar wind flow. During a large CME, the Sun can lose as much mass in a few hours as it normally loses through the solar wind in several days. The study of the solar wind has also revealed unexpected connections between solar activity and Earth's climate. While the total solar irradiance varies by only 0.1% over the solar cycle, the solar wind's intensity varies much more dramatically. Some researchers have found correlations between solar wind conditions and cloud formation, possibly mediated by cosmic rays whose flux at Earth is modulated by the solar wind. Others have identified links between solar wind patterns and atmospheric circulation patterns. While these connections are still being studied and debated, they suggest that the Sun's mass loss might affect Earth's climate in subtle ways beyond simple heating and cooling. As we delve deeper into understanding the solar wind, we're also learning about our place in the galaxy. The heliosphere, inflated by the solar wind, moves through the local interstellar medium like a ship through water, creating a bow shock or bow wave ahead of us. The shape and size of the heliosphere depend on the balance between solar wind pressure and interstellar pressure, and both of these vary as we orbit the galactic center. Sometimes we pass through denser interstellar clouds, compressing the heliosphere. Other times we move through nearly empty voids where the heliosphere can expand. The solar wind is our interface with the galaxy, the boundary between solar and stellar, between home and away. The million tons of matter that the solar wind carries away each second might seem like a loss, a diminishment of our star. But consider what this mass accomplishes as it flows outward. It maintains the heliosphere that protects us from cosmic rays. It strips away atmospheric gases from some planets while delivering particles to others. It makes comets visible, creates aurora, affects weather both in space and possibly on Earth. It carries information about solar conditions throughout the solar system at speeds of hundreds of kilometers per second. This isn't just mass loss, it's communication, protection, interaction. The Sun speaks to its planets through the solar wind, and we're just beginning to understand the language. The future of solar wind research is bright with possibility. New missions are being planned to study the wind from multiple vantage points simultaneously, creating a three-dimensional picture of how it flows and evolves. Advanced models running on supercomputers are beginning to capture the full complexity of the wind's turbulent dynamics. Laboratory experiments are recreating solar wind conditions to test our understanding of the fundamental physics. And as we venture further into space, establishing bases on the Moon and Mars, understanding and predicting the solar wind becomes not just scientifically interesting but crucial for human survival beyond Earth. There's something profoundly peaceful about knowing that the solar wind has been blowing for billions of years, will continue for billions more. Long before Earth formed, the young Sun was already sending out its wind, clearing away the remaining gas and dust from the solar nebula. Throughout Earth's entire history, as continents formed and reformed, as life evolved from single cells to complex organisms, as species arose and went extinct, the solar wind kept flowing, kept pushing outward, kept maintaining that protective bubble we call the heliosphere. And long after humanity's story has ended, the wind will continue, carrying the Sun's substance out into space, a gentle exhalation that never pauses, never stops. When you think about the solar wind, you might imagine it as the Sun's way of touching the entire solar system simultaneously. Unlike sunlight, which travels in straight lines and can be blocked by planets or moons, the solar wind flows around obstacles, fills the entire heliosphere, reaches into every corner of the solar system. It's omnipresent, a constant reminder that we live not near a star but within a star's extended atmosphere. Every planet, every asteroid, every grain of dust in the solar system is immersed in the solar wind, touched by particles that days ago were part of the sun itself. This solar wind also reminds us that the boundary between the sun and space, between star and not star, is not sharp but gradual. There's no clear surface where the sun ends and space begins. The photosphere, what we call the sun's surface, is just where the gas becomes opaque to light. Above it, the chromosphere and corona extend for millions of kilometers, gradually thinning into the solar wind, which extends for billions of kilometers, gradually thinning into the interstellar medium. The sun doesn't have an edge. It fades away, becoming more and more tenuous until it merges with the general interstellar background. We live within this gradual transition, neither fully in the sun nor fully in interstellar space, but in the margin between the two. As you drift deeper into relaxation, perhaps you can imagine the solar wind as a gentle current flowing past Earth, around Earth, continuing on its journey to the stars. Right now, as you listen, particles that left the sun 2 or 3 days ago are streaming past our planet at hundreds of kilometers per second. Some are being caught by our magnetic field, spiraling down toward the poles. Others are continuing outward, heading for the outer planets, the Kuiper belt, the Oort cloud, eventually the heliopause and beyond. Each particle carries a tiny bit of the sun's mass, a tiny bit of its angular momentum, a tiny bit of its magnetic field. Together they represent a constant flow of solar substance into space, a mass loss that shapes and defines our entire solar system. The measurement of mass loss requires extraordinary precision and patience. We can't simply weigh the sun before and after to see how much mass it has lost. Instead, we must infer the loss from its effects, from the energy we receive, from the particles we detect, from the subtle changes in planetary orbits over centuries. It's like trying to measure the water loss from a vast lake by studying the streams that flow from it, the evaporation from its surface, the slowly dropping water level. Every measurement contributes to our understanding, but no single measurement tells the whole story. Scientists have developed ingenious methods to measure what seems unmeasurable. They use the Doppler effect to measure the speed of material moving on the sun's surface, revealing convection patterns and differential rotation. They analyze the spectrum of sunlight to determine the sun's composition, temperature and density at different depths. They measure the subtle gravitational effects of the sun's oblateness, its slight flattening due to rotation, to infer its internal structure. They track the precise positions of planets over decades to detect the tiny changes in orbits caused by the sun's mass loss. Each technique provides a different piece of the puzzle, and together they create a remarkably complete picture of our star's gentle diminishment. The source satellite, the Solar Radiation and Climate Experiment, measured the sun's total irradiance, the total amount of energy Earth receives from the sun, with extraordinary precision. Its instruments could detect changes as small as 0.01%, allowing scientists to track how the sun's energy output varies with the solar cycle, with solar rotation, even with individual sunspots and faculae crossing the sun's disk. These measurements, continued now by the TSIS-1 instrument on the International Space Station, provide the energy side of the mass-energy equation, allowing us to calculate how much mass is being converted to energy through fusion. The precision of modern measurements is staggering. We can now detect changes in the sun's output of just a few parts per million. We can measure the solar wind speed to within a few kilometers per second, its density to within a fraction of a particle per cubic centimeter. We can track planetary positions to within meters over distances of billions of kilometers. We can count individual neutrinos from fusion reactions in the sun's core. This precision allows us to not just detect the sun's mass loss, but to study its variations, its patterns, its relationship to solar activity and stellar evolution. Helioseismology, the study of oscillations on the sun's surface, provides another window into solar mass loss. The sun rings like a bell, with millions of different acoustic modes creating a complex pattern of rising and falling motion on its surface. These oscillations, typically just a few meters in amplitude and lasting minutes to hours, are caused by sound waves bouncing around inside the sun. Just as seismologists use earthquake waves to study Earth's interior, helioseismologists use these solar oscillations to probe the sun's internal structure. They can measure the speed of sound at different depths, the rotation rate of different layers, the size of the convection zone, even the abundance of helium in the core. all from watching the sun's surface jiggle by a few meters. The Global Oscillation Network Group, GONG, operates 6 telescopes around the world to provide continuous observations of the sun's oscillations. By spacing the telescopes in longitude, GONG ensures that the sun is always visible from at least one site, creating an uninterrupted record of solar oscillations spanning decades. This long baseline is crucial for detecting subtle changes in the sun's interior, including the gradual changes caused by mass loss through fusion. As hydrogen is converted to helium in the core, the mean molecular weight increases, changing the speed of sound and thus the frequencies of oscillation. It's an incredibly subtle effect, but with decades of precise observations, it becomes measurable. Space-based helioseismology missions like SOHO and SDO have revolutionized our ability to study the sun's interior. Free from the distortions of Earth's atmosphere, these satellites can detect oscillations with amplitudes of just a few centimeters, revealing ever more detailed information about the sun's internal structure. They've shown us that the sun's core rotates as a solid body, while the surface shows differential rotation, with the equator rotating faster than the poles. They've revealed a thin layer called the tachocline between the radiative and convective zones, where the rotation rate changes dramatically, and where the sun's magnetic field might be generated. They've even detected the subtle effects of individual active regions on the far side of the sun, allowing us to track sunspots before they rotate into view. The combination of neutrino detection and helioseismology has given us unprecedented confidence in our understanding of the sun's interior and its mass loss through fusion. The neutrinos tell us about conditions in the core right now, while helioseismology reveals the integrated effects of billions of years of fusion. When both methods give consistent results, and they do, beautifully, we know our models are on the right track. We can say with confidence that the sun is converting 620 million tons of hydrogen to 616 million tons of helium every second, with the missing 4 million tons becoming energy. But measuring the solar wind's mass loss requires different techniques. We can directly sample the solar wind at Earth's orbit using spacecraft measuring its density, speed and composition. But the wind isn't uniform. It varies with solar latitude, with the solar cycle, with individual events on the sun. To get a complete picture, we need measurements from multiple locations. The Ulysses spacecraft, which flew over the sun's poles, showed that the solar wind from polar regions is quite different from the equatorial wind we usually sample. The twin stereo spacecraft, observing the sun from ahead and behind Earth in its orbit, provided the first three-dimensional views of the solar wind structure. Future missions promise even more detailed measurements. The proposed interstellar probe would travel beyond the heliopause to look back at our heliosphere from outside, finally revealing its true shape and size. Constellations of small satellites could sample the solar wind at many points simultaneously, creating real-time maps of its structure and evolution. Advanced coronagraphs could track the solar wind from its birth in the corona to its arrival at Earth, following individual parcels of gas as they accelerate outward. Each new measurement capability reveals new aspects of how our sun loses mass, how it breathes out into space. The implications of solar mass loss extend far beyond our solar system. When we observe other stars, we see evidence of similar processes: stellar winds detected through their interaction with surrounding gas, absorption lines blue-shifted by outflowing material, bow shocks where stellar winds collide with the interstellar medium. Young stars show powerful winds that clear away their birth nebulae. Evolved stars shed their outer layers through slow, dense winds. Binary stars exchange mass through wind interaction. Everywhere we look, stars are losing mass, breathing out into space just as our sun does. This universality suggests that mass loss is not an unfortunate imperfection, but a fundamental aspect of how stars work. A star that didn't lose mass would be fundamentally different from the stars we observe. It would have no wind to clear away its birth nebula, no way to enrich the interstellar medium with heavy elements, no mechanism to lose angular momentum and spin down over time. Mass loss is as essential to stellar evolution as fusion itself. The sun's gentle loss of 4 million tons per second through fusion and another million tons through the solar wind is not a flaw, but a feature, a necessary aspect of being a star. The study of solar mass loss has also revealed unexpected connections between different areas of physics. The solar wind is a natural laboratory for plasma physics, demonstrating phenomena that can't be reproduced in Earth-based laboratories. The interaction between the solar wind and planetary magnetospheres involves quantum mechanics, relativity, and classical electromagnetism all at once. The propagation of energetic particles through the heliosphere connects to cosmic ray physics and galactic astronomy. The Sun's mass loss touches on nuclear physics, thermodynamics, magnetohydrodynamics, spectroscopy. Almost every branch of physics contributes to our understanding of this process. As you continue to relax, perhaps letting these ideas flow through your mind like the solar wind flows through space, consider how the measurement of something as seemingly simple as mass loss reveals the deep interconnectedness of natural phenomena. To understand why the Sun loses 4 million tons per second, we need to understand nuclear fusion, stellar structure, convection, radiation, magnetic fields, plasma physics, and more. Each piece of understanding builds on others, creating a web of knowledge as complex and beautiful as the physical processes themselves. The technology required to measure solar mass loss represents some of humanity's greatest achievements. The neutrino detectors are marvels of engineering, requiring thousands of tons of ultra-pure materials, sophisticated electronics that can detect single photons, locations deep underground to shield from cosmic rays. The space telescopes that observe the Sun operate in extreme environments, some close enough to melt lead, others in the cold darkness beyond Pluto. The computer models that simulate solar processes require some of the world's most powerful supercomputers, solving equations that describe physics from the quantum to the cosmic scale. All of this effort, all of this ingenuity devoted to understanding a process that happens, whether we observe it or not, the Sun's quiet loss of mass. There's something humbling about the precision with which we can now measure cosmic processes. We can detect the Sun's surface moving up and down by a few centimeters from 150 million kilometers away. We can count individual neutrinos that have traveled through 150 million kilometers of space and thousands of kilometers of rock. We can measure the solar wind's density to a fraction of a particle per cubic centimeter in a volume of space larger than Earth. These measurements would have seemed like magic to scientists just a century ago, yet they're routine today, part of our ongoing effort to understand our place in the cosmos. The continuity of these measurements over decades is equally impressive. Some solar observations have been made daily for over a century. The sunspot record extends back over 400 years. Tree rings and ice cores preserve information about solar activity going back millennia. This long baseline allows us to see patterns and changes that would be invisible in shorter observations. We can track the 11-year solar cycle, the longer-term grand minima and maxima, the slow evolution of the Sun's magnetic field. Each day's observations add to this growing record, building our understanding increment by increment. As we contemplate these measurements, it's worth remembering that they're made by people, scientists and engineers who dedicate their careers to understanding the Sun. Behind every data point is a human story, the graduate student analysing their first solar spectrum, the engineer solving a problem with a spacecraft's instruments, the theorist working out the implications of a new observation. Science is a human endeavour, and our understanding of the Sun's mass loss is the product of countless human minds working together across generations, across cultures, across disciplines. The international nature of solar research is particularly striking. The Sun belongs to no single nation, and understanding it requires global cooperation. Japanese scientists build neutrino detectors, European scientists launch solar observatories, American scientists develop theoretical models, Chinese scientists operate solar telescopes, Indian scientists analyze solar wind data. The Sun rises on every nation, and every nation contributes to our understanding of it. This cooperation transcends political boundaries, economic systems, and cultural differences, united by the common goal of understanding our star. Looking ahead, the future of solar mass loss studies is bright with possibility. New technologies promise even more precise measurements. Gravitational wave detectors might one day be sensitive enough to detect the Sun's oscillations directly. Neutrino telescopes could map the fusion reactions in the Sun's core in 3 dimensions. Interstellar probes could measure the solar wind from outside the heliosphere. Each new capability will reveal aspects of solar mass loss we haven't yet imagined, answering current questions while undoubtedly raising new ones. But perhaps the most profound aspect of studying the sun's mass loss is what it tells us about time and change. The sun has been losing mass for 4.6 billion years and will continue for billions more. This process spans timescales so vast that all of human history is but an instant, yet we can measure it, understand it, predict it. We are ephemeral beings studying an almost eternal process, using our brief moment of consciousness to comprehend something that transcends our existence by factors of billions. There's a deep beauty in this, a kind of cosmic poetry in our ability to know about processes we can never fully witness. As you drift towards sleep, perhaps you can feel yourself connected to this vast, slow process. The warmth in your room, the energy in your body, the thoughts in your mind, all of it powered by the sun's mass loss, by those 4 million tons per second converted to energy, by that million tons per second blown into space as solar wind. You're not separate from this process, but part of it, a temporary arrangement of matter and energy made possible by the sun's patient sacrifice. Every atom in your body except hydrogen was forged in the cores of stars that, like our sun, converted mass to energy and eventually dispersed that matter into space. Your star stuff contemplating stars, a way for the cosmos to know itself. The measurement of the sun's mass loss is ultimately a measurement of the process that makes everything possible. Without stars converting mass to energy, the universe would be dark and cold. Without stellar winds dispersing heavy elements, there would be no planets, no chemistry, no life. The 4 million tons per second that our sun loses is not a loss, but an investment, a transformation that creates the possibility of everything we know and are. In measuring this loss, we measure the generosity of the cosmos, the patient process by which simple hydrogen becomes complex life, by which mass becomes energy, becomes consciousness contemplating its own origin. As we transition to contemplating the deeper implications of the sun's mass loss, consider how this knowledge changes our perspective on existence itself. We are not living near a permanent, unchanging star, but rather in the presence of a slowly transforming stellar engine that powers everything we experience. The sun's mass loss is the heartbeat of the solar system, the fundamental rhythm to which all other processes dance. Tomorrow, when you wake, the sun will be lighter by about 350 billion tons than it is right now, yet it will rise just as it always has, warm the earth just as it always has, continue its patient work of transformation just as it has for billions of years. The sun grows lighter, and in response, the entire architecture of our solar system adjusts with extraordinary subtlety. Every planet, every moon, every asteroid and comet feels the effects of the sun's diminishing mass, their orbits expanding outward by amounts so small that centuries of precise observation are required to detect the change. Yet this change is real, measurable, and profound in its implications for the long-term evolution of our cosmic neighborhood. As you settle deeper into rest, let's explore this slow, graceful dance of celestial mechanics, where the loss of 4 million tons per second translates into a gradual loosening of gravity's embrace. Consider Earth's orbit around the Sun, that nearly circular path we travel once each year, covering about 940 million kilometers at an average speed of 30 kilometers per second. This orbit, which seems so fixed and eternal from our perspective, is actually slowly spiraling outward as the Sun loses mass. The physics is beautifully simple. As the Sun's mass decreases, its gravitational pull weakens, and Earth responds by moving to a slightly larger orbit. Currently, Earth's orbit is expanding by about 1.5 centimeters per year, less than the length of your thumb, spread over a path nearly 1 billion kilometers long. This might seem impossibly small, negligible, not worth considering. But over geological time, these tiny annual increases accumulate into significant changes. In 1 billion years, if the current rate continues, Earth will be about 15,000 kilometers farther from the Sun than it is today. That's more than the diameter of Earth itself, enough to measurably affect the amount of sunlight we receive, the length of our year, the stability of our climate. The Sun's mass loss is gradually reshaping the solar system's architecture, even if the changes are too slow for any single generation of humans to perceive directly. The relationship between the Sun's mass and planetary orbits follows Kepler's laws, those elegant mathematical relationships discovered 4 centuries ago by Johannes Kepler as he studied the motion of Mars. The third law tells us that the square of a planet's orbital period is proportional to the cube of its average distance from the Sun, divided by the Sun's mass. As the Sun's mass decreases, planets must move outward to maintain this relationship, their years growing longer as their orbits expand. It's like a cosmic dance where the music is gradually slowing down and all the dancers must adjust their steps accordingly. Mercury, the innermost planet, feels the effects most strongly in absolute terms because the Sun's gravity is strongest there. But proportionally, all planets experience the same fractional change in their orbits. Mars, Jupiter, Saturn, each is slowly drifting outward, their years growing imperceptibly longer. Jupiter's year, already nearly 12 Earth years long, increases by about a millisecond per century. Saturn's year grows by about 2 milliseconds per century. These changes are so small that they're lost in the noise of other gravitational perturbations, but they're real, accumulating steadily as the Sun continues its patient transformation of mass into energy. The measurement of these orbital changes requires extraordinary precision and patience. Astronomers track planetary positions using radar ranging, where radio signals are bounced off planets and the return time measured to determine distance. They use very long baseline interferometry, combining observations from radio telescopes thousands of kilometers apart to achieve angular resolutions better than a milliarc second. They analyze centuries of optical observations, carefully accounting for improvements in telescope technology and measurement techniques. Each method contributes to our understanding of how planetary orbits are evolving in response to solar mass loss. The Cassini spacecraft, during its 13-year mission at Saturn, provided some of the most precise measurements of orbital evolution ever made. By tracking Cassini's position relative to Saturn and Saturn's position relative to the Sun with extraordinary accuracy, scientists could detect tiny changes in Saturn's orbit. Combined with similar measurements from spacecraft at Mars, Jupiter and Mercury, these observations confirm that planetary orbits are indeed expanding as predicted by solar mass loss. The agreement between observation and theory is remarkable, a testament to our understanding of both stellar physics and celestial mechanics. But it's not just planetary orbits that are affected. Every object in the solar system, from the largest moon to the smallest grain of dust, feels the effects of the Sun's decreasing mass. The asteroid belt slowly expands outward. Comets in the Kuiper belt see their orbital periods grow longer. Even the hypothetical Oort cloud, that vast sphere of icy bodies surrounding our solar system at distances of up to a light year, gradually loosens as the Sun's gravitational grip weakens. The entire solar system is slowly puffing up like a balloon being inflated, though the inflation is so slow that it would take billions of years to double in size. This expansion has interesting implications for the stability of the solar system. Some orbits that are stable today might become unstable in the far future as the Sun loses mass. Conversely, some objects currently in unstable orbits might find stability as the system expands. The complex gravitational dance of planets, moons and smaller bodies evolves not just through their mutual interactions but also through the slow weakening of the Sun's gravity. Computer simulations extending billions of years into the future show that while the inner solar system should remain stable, the outer planets might experience more significant orbital changes as the Sun evolves and loses mass more rapidly in its later stages. The Moon's orbit around Earth provides another fascinating example of orbital evolution, though here the dominant effect is not solar mass loss but tidal friction. The Moon is receding from Earth at about 3.8 centimeters per year, primarily due to tidal interactions that transfer angular momentum from Earth's rotation to the Moon's orbit. But superimposed on this is a tiny effect from solar mass loss, which affects the Earth-Moon system's orbit around the Sun. As our mutual orbit around the Sun expands, the dynamics of the Earth-Moon system subtly change, adding another layer of complexity to an already intricate gravitational relationship. Scientists have used ancient eclipse records to study these orbital changes over historical time. Chinese astronomers recorded eclipses over 3,000 years ago with sufficient precision that we can compare their observations with modern calculations. The differences reveal how Earth's rotation has slowed and how the Moon's orbit has evolved. While solar mass loss contributes only a tiny fraction of these changes, it must be included in the calculations to achieve perfect agreement between ancient observations and modern theory. Every effect, no matter how small, contributes to the full picture. The slow expansion of planetary orbits also affects the habitable zone, that region around a star where liquid water can exist on a planet's surface. As the Sun loses mass and planets move outward, they maintain roughly the same position relative to the habitable zone, which also moves outward as the Sun gradually brightens. It's a cosmic coincidence that helps maintain planetary climates over geological time. If planets didn't move outward as the Sun brightened, Earth would have become too hot for life long ago. This self-regulating aspect of stellar and orbital evolution might be crucial for the development of complex life, providing the stable conditions needed for billions of years of evolution. Looking far into the future, the effects of solar mass loss become even more pronounced. In about 5 billion years, as the Sun exhausts its hydrogen fuel and begins to evolve into a red giant, it will lose mass much more rapidly through an enhanced solar wind. Models suggest the Sun might lose 30% or more of its current mass during this phase. Planetary orbits will expand dramatically. Earth's orbit might grow by 50% or more, potentially saving our planet from being engulfed by the expanding Sun. Mars might find itself in the habitable zone for the first time in billions of years. The outer planets will drift even farther into the cold darkness, their orbits becoming ever more elongated and unstable. The study of orbital evolution due to mass loss extends beyond our solar system. When we observe exoplanets around other stars, we must account for the mass loss of their host stars to understand their long-term orbital evolution. Hot Jupiters, orbiting close to their stars, experience not just gravitational effects, but also atmospheric stripping from stellar winds, adding another dimension to their orbital evolution. Binary stars exchanging mass show dramatic orbital changes, sometimes spiraling together, sometimes flying apart. Every stellar system is dynamic, evolving in response to the mass loss of its stars. The precision with which we can now predict these orbital changes is a triumph of celestial mechanics. Using Einstein's general relativity for the strongest gravitational fields and Newtonian mechanics for more distant orbits, we can calculate planetary positions millions of years into the past or future with remarkable accuracy. These calculations must account not just for solar mass loss, but for countless other effects, perturbations from other planets, relativistic corrections, tidal forces, even the pressure of sunlight on planetary surfaces. Each effect is tiny, but together they determine the precise paths planets follow through space. The Gravity Recovery and Climate Experiment, GRACE satellites, have shown us that we can measure gravitational changes with extraordinary sensitivity. While GRACE focuses on Earth's gravity field, similar techniques could potentially measure the Sun's decreasing mass directly by tracking the tiny changes in spacecraft orbits over time. Future missions might use laser interferometry between multiple spacecraft to detect the gradual weakening of the Sun's gravity, providing direct confirmation of the mass loss we currently infer from energy output and particle emissions. As you contemplate these vast, slow changes, consider how they connect to the rhythms of your own life. The length of a day, the length of a year, the cycle of seasons, all of these are gradually changing due to the Sun's mass loss and other astronomical effects. Each year is about 5 microseconds longer than the last due to Earth's expanding orbit. Each day is about 2 milliseconds longer per century due to tidal friction. These changes are far too small to notice in a human lifetime, but they accumulate over geological time. The dinosaurs experienced days that were about 30 minutes shorter than our current days, years that were a few hours shorter than our years. This gradual evolution of time itself, the lengthening of days and years, connects us to the deep history of our planet and the slow transformation of our star. We live in a particular moment of this evolution, experiencing days and years of particular lengths that are unique to our epoch. Future beings, whether human or otherwise, will experience slightly different rhythms, slightly different relationships between rotation and revolution, between day and night, between the seasons. The Sun's mass loss is slowly rewriting the fundamental periods that govern life on Earth. The implications extend to our search for life elsewhere in the universe. When we look for potentially habitable exoplanets, we must consider not just their current orbits, but how those orbits will evolve as their stars lose mass. A planet that's too cold today might be perfectly positioned in a billion years. A planet that's habitable now might become too hot or too cold in the future. The habitable zone is not a fixed region, but a moving target, and planets can drift into or out of it over geological time. Understanding stellar mass loss is crucial for assessing the long-term habitability of other worlds. The slow expansion of the solar system also affects the delivery of water and organic molecules to planets. Comets, those icy messengers from the outer solar system, have orbits that evolve in response to solar mass loss. As their orbits expand, the frequency and velocity of comet impacts on inner planets change. This might affect the delivery of volatiles to terrestrial planets, potentially influencing their ability to develop and maintain atmospheres and oceans. The same process that makes the sun shine, mass conversion to energy, also governs the long-term delivery of the very molecules that make life possible. Space missions must account for these orbital changes in their long-term planning. The Voyager spacecraft, launched in 1977, have travelled so far that the accumulated effects of solar mass loss on their trajectories are measurable. Future interstellar missions lasting centuries or millennia will need even more precise accounting for the sun's decreasing gravity. Navigation in the far future will require models that include not just current orbital mechanics, but predictions of how those mechanics will evolve as stars lose mass. The discovery that orbits expand due to stellar mass loss has philosophical implications as well. It shows us that the cosmos is not static but dynamic at every scale. Even something as seemingly permanent as Earth's orbit around the Sun is slowly changing, evolving, responding to the gradual transformation of our star. This cosmic impermanence might seem unsettling, but it's also liberating. Nothing is fixed, everything is in process, and we are witnesses to and participants in this vast, slow dance of matter and energy, gravity and motion. The mathematical beauty of these orbital changes is striking. The equations that govern them are elegant and simple, yet their implications are profound and far-reaching. The same inverse square law that Newton discovered by considering falling apples and orbiting moons applies equally to the slow expansion of planetary orbits due to solar mass loss. The universality of these physical laws, their applicability across vast ranges of scale and time, speaks to a deep order in the universe. The sun loses mass, gravity weakens, orbits expand, all according to mathematical relationships that we can write on a single page. As we observe other stellar systems at different stages of evolution, we see this process playing out across the galaxy. Young stars with protoplanetary disks losing mass through powerful winds, clearing gaps that will become planetary orbits. Main sequence stars like our Sun slowly losing mass through fusion and stellar winds, their planets gradually spiraling outward, red giants shedding their outer layers, their planets, if they survive, suddenly finding themselves in vastly expanded orbits. White dwarfs, having lost most of their mass, retaining only distant, loosely bound planets in cold, dark orbits. Each system is a snapshot of a dynamic process, a moment in the long evolution driven by stellar mass loss. The connection between stellar mass loss and orbital dynamics also helps us understand the formation of planetary systems. As young stars lose mass through powerful winds, they clear away the remaining gas and dust from their protoplanetary disks, ending the epoch of planet formation. The orbits that planets end up in depend partly on how quickly their star loses mass during this clearing phase. Too fast, and planets might be destabilized or ejected. Too slow, and remaining gas might cause planets to spiral inward. The rate of stellar mass loss is thus a crucial factor in determining the architecture of planetary systems. Recent observations of protoplanetary disks around young stars have revealed this process in action. The Atacama Large Millimeter Array, ALMA, has imaged gaps and rings in these disks, showing where planets are forming and how stellar winds are clearing material. The Hubble Space Telescope has detected jets and outflows from young stars, direct evidence of mass loss during the planet-forming epoch. These observations show us that the process affecting our mature solar system, orbital expansion due to stellar mass loss, begins from the very moment planets form. The interplay between stellar mass loss and orbital dynamics extends to galactic scales as well. Stars orbiting the galactic center experience the combined mass loss of billions of stars, causing a gradual expansion of the galaxy itself. Globular clusters slowly evaporate as their stars lose mass and their mutual gravity weakens. Even clusters of galaxies feel the effects, their dynamics evolving as their constituent galaxies lose mass through stellar winds and radiation. The same process we observe in our solar system, orbits expanding due to mass loss, operates at every scale in the universe. As you drift closer to sleep, perhaps you can imagine the solar system as a slowly opening flower, its planetary petals gradually spreading as the sun grows lighter. This is not a violent or sudden change, but a patient unfolding that has been happening since the planets formed and will continue until the sun's final days. Each planet traces its expanding spiral through space, maintaining its relationship with its siblings even as they all drift slowly outward. It's a cosmic ballet performed in extreme slow motion, beautiful in its mathematical precision and physical inevitability. The measurement of these orbital changes represents one of humanity's most precise achievements. We can detect changes in planetary positions of less than a meter over distances of billions of kilometers. We can measure changes in orbital periods of microseconds in years that are centuries long. This precision allows us to test our theories of gravity and stellar evolution to extraordinary accuracy. Every successful prediction, every agreement between theory and observation, increases our confidence that we truly understand how stars lose mass and how that loss affects the worlds around them. The future promises even more precise measurements. The Gaia spacecraft is measuring the positions and motions of billions of stars with unprecedented accuracy, allowing us to see how entire stellar systems evolve in response to mass loss. The James Webb Space Telescope is observing young planetary systems in formation, showing us the beginning of the process that will eventually lead to orbital expansion. Future gravitational wave observatories might detect the slow inspiral of binary stars losing mass, providing yet another window into this fundamental process. But perhaps what's most remarkable is that we can know any of this at all. We are beings that live for decades studying processes that unfold over billions of years. We occupy a single planet orbiting a single star, yet we can understand the orbital evolution of planetary systems throughout the universe. The same intelligence that evolved to help our ancestors survive on the African savanna now comprehends the slow expansion of planetary orbits due to stellar mass loss. There's a profound beauty in this, a testament to the power of curiosity and reasoning to transcend the limitations of our immediate experience. The practical implications of understanding orbital evolution due to solar mass loss extend beyond pure science. As we plan for humanity's future in space, whether on Mars, the Moon, or in orbital habitats, we need to understand how the solar system will evolve over long timescales. Will Mars still be cold in a billion years? Will the asteroid belt remain stable? How will the orbits of near-Earth asteroids evolve? These questions matter for the long-term survival and expansion of life beyond Earth. Understanding solar mass loss and its effects is not just an academic exercise, but potentially crucial knowledge for our species' future. The slow expansion of planetary orbits also provides a natural clock, a way to measure the passage of cosmic time. Just as we use radioactive decay to date rocks and carbon-14 to date organic materials, we could in principle use orbital expansion to date astronomical events. The current orbital configuration of the solar system tells us how long the Sun has been losing mass at its current rate. Deviations from expected orbits might reveal past events, close encounters with other stars, passages through dense interstellar clouds, or changes in the Sun's mass loss rate. The planets are not just worlds but chronometers, keeping time on scales that dwarf human history. As we consider these vast timescales and slow changes, it's worth reflecting on what they mean for our sense of place in the universe. We're not living in a fixed, eternal cosmos, but in a dynamic, evolving one. The ground beneath our feet is slowly spiraling outward. The sun that warms us is gradually growing lighter. The year that marks our birthdays is gradually growing longer. Yet these changes are so slow that for all practical human purposes, they might as well not exist. We live in the tension between cosmic change and apparent stability, between the dynamic and the static, between becoming and being. This tension is perhaps nowhere more apparent than in our emotional response to learning about solar mass loss and orbital evolution. On one hand, there's something unsettling about learning that Earth's orbit is not fixed, that we're slowly drifting away from the Sun. On the other hand, there's something deeply reassuring about the slowness of the change, the fact that it will take billions of years for any significant effects to manifest. We are safe in our cosmic moment, even as we participate in a process of gradual transformation that spans eons. The story of discovering orbital evolution due to solar mass loss is also a story about human persistence and ingenuity. It took centuries of observations, generations of scientists and tremendous technological advancement to detect and understand these tiny changes. Each generation built on the work of the previous one, adding their observations to the growing record, refining the theories, improving the instruments. The detection of orbital expansion due to solar mass loss is not the work of any individual, but the culmination of humanity's collective effort to understand our cosmic home. As you approach the edge of sleep, perhaps feeling your consciousness beginning to drift like a planet in an expanding orbit, consider one final thought about the sun's mass loss and its effects on the solar system. Every second, as 4 million tons of solar mass becomes energy, and another million tons streams away as solar wind, the entire architecture of our cosmic neighborhood adjusts itself with perfect mathematical precision. No force is required, no intervention needed, just the natural response of matter to changing gravitational fields, playing out according to laws that have operated since the universe began. Tomorrow, Earth will be a few centimeters farther from the sun than it is today. Your next birthday will come a few nanoseconds later than it would have if the sun weren't losing mass. These changes are too small to notice, too small to matter in any practical sense, yet they're real, measurable, and profound in their implications. We live in a solar system that is slowly, gently expanding, carrying us on a gradual outward spiral that will continue for billions of years. It's a journey we're all on together. Every planet, every moon, every asteroid and comet, slowly drifting outward as our star grows lighter, participating in a cosmic dance whose music is the patient conversion of mass into energy. 4 million tons per second, every second, until the end of the sun's days.